Hi, welcome to Signals and Systems course. This chapter, we are going to discuss about information systems and fundamentals. Signals and systems form a foundational pillar in various fields of engineering and applied science, from telecommunications and control engineering to biomedical signal processing. A signal can be viewed as a function that conveys information about the behavior or attributes of a physical phenomenon. When these signals are fed into a system, the system is a collection of components or a mathematical model designed to process input signals. This system produces a corresponding output signal. Understanding how signals are represented, how systems respond to these signals, and how both signals and systems are analyzed in different domains, time and frequency, is essential for designing and interpreting a wide range of engineering applications. In this course, we place a strong emphasis on continuous time signals, which are defined for every real value of time. Continuous time signals are central to many real-world applications, such as analog communications and natural phenomena, for example, temperature changes, acoustic waves, electrical signals. In contrast, discrete time signals are defined only at specific time instants and often arise from sampling continuous signals. While discrete time concepts will also be mentioned, especially when exploring the transition from analog to digital domains, the primary focus here will be on analyzing continuous time signals and systems. A key theme of this course is the twofold approach to analysis: the time domain perspective and the frequency domain perspective. In the time domain, we often use tools like differential equations to characterize system behavior and employ convolution to determine the output of linear time invariant LTI systems in response to various inputs. For instance, an LTI system can be completely described by its impulse response, and the output for any given input can be found by convolving the input with this impulse response. Moving to the frequency domain opens up a powerful set of methods that provide insight into how a system behaves with respect to different frequencies. Normal frequency analysis involves the use of the Fourier series for periodic signals and the Fourier transform for aperiodic signals to decompose signals into sinusoids. We will discuss more about periodic and aperiodic signals in the following slides or chapters. This decomposition reveals each frequency component's amplitude and phase, helping us understand signal bandwidth, filtering characteristics, and resonance behaviors. For more advanced analysis, especially when dealing with transient responses, stability, and control related problems, we employ complex frequency analysis via the Laplace transform. The Laplace transform simplifies the handling of differential equations and provides a straightforward way to analyze system stability and transient behavior by examining poles and zeros in the complex plane. Throughout this course, you will encounter various real-world examples illustrating how continuous time signals are processed into different engineering applications, from simple RC circuits and analog filters to more complex control systems. The fundamental principles remain consistent: represent the signal, model the system, and use the appropriate analysis technique, time domain or frequency domain, to determine the behavior of the output. By mastering these concepts, you will gain a deeper understanding of how information flows through systems, how signals can be manipulated to extract or encode data, and how to design systems that meet desired performance criteria. This framework sets the stage for the detailed topics outlined in the course schedule. You will learn to classify signals based on their properties: periodic, aperiodic, deterministic, or random. Explore the defining characteristics of systems: linearity, time invariance, causality, stability, and apply mathematical tools like convolution, differential equations, and transforms to solve practical problems. By the end of this course, you will be equipped with the core theoretical knowledge and analytical skills necessary to tackle a wide range of challenges in signals and systems. So let's talk about fundamentals of information systems first. What are data, information, and knowledge? Data is unprocessed facts without any added analysis. Information is the data that has been interpreted so that it has a meaning for the user or designer. And knowledge is a combination of information that may benefit the individual or the organization. So, how to convert data to information? Data becomes information when it is applied to some purpose and adds value for the recipient. For example, a set of raw sales figures is data. It is the sales report that provides information. Collecting data is really expensive. You need to be very clear about why you need it and how you plan to use it. One of the main reasons that organizations collect data is to monitor and improve performance. To be useful, data should satisfy a set of conditions. The data should be complete, accurate, and timely. It should be in the right format and available at a suitable price. Information can only be analyzed using a spreadsheet if all the data can be entered into the computer system. Converting information to knowledge also has some criteria. Ultimately, the tremendous amount of information that is generated is only useful if it can be applied to create knowledge within the organization. Uh, think of knowledge as being of two types: formal, explicit, or generally available knowledge. This is knowledge that has been captured and used to develop policies and operating procedures, for example, or hidden knowledge. Within the organization, there are certain people who hold specific knowledge or have the know how. Clearly, both types of knowledge are essential for the organization. The right information fuels the development of intellectual capital, which in turn drives innovation and performance improvement. A system can be broadly defined as an integrated set of elements that accomplish a defined objective. People from different engineering disciplines have different perspectives of what a system is. For example, for software engineers, it can be a set of computer programs. For electrical engineers, it can be a complex integrated circuits. As can be seen, system depends on one's perspective and the integrated set of elements that accomplish a defined objective. A system is defined as multiple parts working together for a common purpose or goal. Systems can be large and complex, such as the air traffic control system or a global telecommunication network. Small devices can also be considered as systems, such as a calculator or an alarm clock. Systems have inputs, processes, outputs, and feedbacks. When feedback is involved, that component is also important to operation of the system. To explain all this, systems are usually explained using a model. A model helps to illustrate the major elements and their relationship, as seen in this diagram. So what's a digital system? Digital system takes a set of discrete information, inputs, and discrete internal information, system state, and generates a set of discrete information, outputs. An information variable represented by physical quantity. Here, inputs, outputs, and system states transferred are named as signals. The signal defined for each time value t is called a continuous time signal and is denoted as x of t. On the other hand, the signal defined for certain discrete time values is called a discrete time signal. A discrete time signal is expressed as a sequence of numbers and is denoted as x of n, where n is an integer. Time t is divided into n discrete time intervals. A digital signal is very similar to a discrete signal, but the amplitude of a digital signal is quantized at certain levels. This is because digital computers can only accept sequences of numbers expressed in bits. You can see the representation of a digital signal in the figure. At any discrete time interval, the amplitude can only be one of the quantization levels. If the amplitude is chosen from a limited set of numbers, this means that the amplitude is discretized. The quantization levels are equally spaced and are called quantization steps. An analog signal can be converted to a digital signal by sampling and quantization. During this process, the signal value is rounded to the nearest allowed level and converted to digital form. Therefore, a quantization error occurs when an analog signal is discretized and quantized. A digital signal is discretized in time and quantized in amplitude. Analog signal is sampled in every ts seconds. Ts is referred to as the sampling interval. And also, 1 divided by Ts is called the sampling rate or sampling frequency. According to Nyquist theorem, we'll discuss later about them again. The sampling rate must be at least two times the highest frequency contained in the signal. Here, each zones between quantization levels are defined as quantization zones. Each zone is then assigned a binary code. The number of bits required to encode the zones, or the number of bits per sample, is it is commonly referred to, is obtained as follows. Here, L equals to 5. For our example, 2.32, which can be rounded up to 3, which means that we have 2 to the power of 3 zone codes. Then we can identify an analog signal as a digital signal. This process is called analog to digital conversion, or ADC. ADC consists of four steps to digitize an analog signal: filtering, sampling, quantization, and binary encoding. We have done all of it respectively. When a signal is quantized, we introduce an error because the coded signal is an approximation of the actual amplitude value. The difference between actual and coded value is referred to as the quantization error. The more zones results in smaller errors, but the more zones, the more bits required to encode the samples, which means we need higher bit rate. Unsigned binary integers are binary numbers that represent only non-negative values, using only zeros and ones without a dedicated sign bit. In an n-bit unsigned binary system, every bit contributes to the magnitude of the number, allowing for a range from 0 to 2 of the power n minus 1. This means that with 8 bits, for example, the numbers can range from 0 to 255. Because there is no need to reserve a bit for indicating positive or negative, unsigned binary integers maximize the positive range available for a given bit width. These numbers are widely used in digital systems and computing, particularly in applications where only non-negative values are required, such as memory addressing, counters, and digital timers. Converting an unsigned binary number to its decimal form involves multiplying each bit by 2 raised to the power of its positional index and summing the results. This straightforward representation and conversion method makes unsigned binary integers a fundamental concept in computer science and electrical engineering. An additional resource will be added as a link. So this is the only introduction of signals and systems and the end of the chapter 1. In the next chapter, we are going to discuss mathematical representation of signals and systems. So bye for now.